In this lesson, we're looking at continuity. In some ways, this is a very simple idea. The idea is if a function is continuous, you can draw the thing without lifting up your pencil. So if I'm drawing along and I have to jump down somewhere else on my graph, we could say there's a discontinuity at that point. Now, if we're talking about continuity at a point, one thing is that we only need to look at interior points. So if my function is only going from A to B, I would not say there's a discontinuity because I'm starting my drawing at A, I'm tracing it until B, and I'm stopping. And so there's no discontinuity on this interval because I'm not jumping to some other point. This is the complete function. Now, there are different ways that points can be discontinuous. So let's look at some of these on the next page. Now, this would be a removable discontinuity where I have an open dot here at 1 or at 0, 1. Maybe we see that it's up here jumping up to 2, or maybe it's just not there. Now, in either one of these cases, I could remove it simply by changing the definition of my function to fill in the dot or to move the point down there. So it's easy to change. We're not really changing most of the function, we're just filling in a hole. This one, on the other hand, or any of these on the bottom, we have would be a major change in our function to do that. Like here we're jumping up from 0 to 1, jump discontinuity. In infinite discontinuity, since this is a vertical asymptote line, these are never going to meet. When we have an oscillating discontinuity, it's going up and down very crazy and they're just never going to come together. We don't know what they're going to do. Now, if we're looking for continuity at a point, a lot of times we'll look in the same way that we look for asymptote lines or other things that might cause this problem, like zeros in the denominator. Maybe we could look at negative roots and things like that. So in this one, the problem that we might have is having a 1 in the denominator. We can't have x equal to 1. So notice in our graph over here, we're getting a discontinuity at x equals 1. And it's an infinite discontinuity because if we analyze the graph, look at what it's doing, we see that this is a vertical asymptote line. Now this is where it gets a little bit weird. If we use the phrase continuous function, we might have a discontinuity in our function and still call it continuous. Huh? Well, what we're talking about when we define a continuous function is that it's continuous at every part of its domain. So if the point's not in its domain, even though we have a discontinuity, the function itself is whole and complete. So as I'm tracing this function here and come to here, I get to the point -2, which is not in the domain. I have to lift my pencil and move over here to continue tracing this function. We're still going to say it's a continuous function because it's continuous at every point in its domain. So example of continuity at a point. Now this is looking at the idea of a continuous function. So if we look at this, notice we're only going from 0 to 6. So starting at 0, we would say it is continuous because that's our starting point. If we look at 6, that's our finishing point. So again, we are continuous at 6. We don't continue beyond there. And we could also say that we're continuous from 0 to 6 as long as we exclude 2 and 3. Notice 2 is an open dot, so they use an equal sign there. Now, we do have a discontinuity at x equals 2, and we have a discontinuity all along the interval from 2 to 3. And we could also say, if we're not talking about the function, but we're talking about discontinuities, we say it's discontinuous at anything beyond that or anything before that. However, we still say that f is a continuous function because 2 to 3 is not in the domain. One last part of continuous function is just looking at the ways that they can be combined. So as long as we're looking in the domain, same domain, if they're continuous at a certain point, we can add them, we can subtract them, we can multiply them, divide them, make composite functions, and we'll still have continuous functions when we're finished.